So I just want to welcome you to this technical talk on the last day of the summit. Rohini and I are both PMCs in Apache, her with Pig and I in Tez. And we both work at Yahoo, and this is our experience of running Pig on Tez at Yahoo scale. This is just a brief overview of where we're going to be going today. So with the introduction of Yarn came the promise of processing that was not limited by the constraints of MapReduce, namely two-stage processing, processing that could be fully represented in a single application, processing that could have multiple inputs and multiple outputs, processing that could shuffle intermediate data from map to reduce to further reduces efficiently and eloquently. And with this talk, I hope to help show you the progress of that promise with Yahoo's experience of running Pig on Tez at scale. Just want to take a brief overview of looking at this chart just so we can kind of have the same vocabulary going through this chart, through this talk today. So MapReduce, of course, is on your left, and that's just, I think we're all pretty much familiar with the way this runs. A single Pig script is going to be broken down into multiple MapReduce stages with intermediate data being written to HDFS. That's what the clouds represent. Maps are blue in this picture, as well as reduces are green. And on the, of course, right-hand side is Tez, and that's kind of where we need to go. Each of the stages are called vertices. Again, map-like vertices are blue, reduce-like vertices are green, and you can notice that only the final data is written to HDFS, and while all other intermediate data is shuffled through local disk and is a little bit more efficient. So why Tez, and specifically why Pig on Tez? So if you've been around these big data conferences for any time at all, you'll know that Yahoo runs Pig probably more than anyone in the world at this point. And so that's kind of the why Pig answer. Why Tez is a slightly more subtle answer, and I want to just take a brief moment to address this so that you can get the whole picture. I think if we miss this moment, it'll be hard to kind of put the rest of this talk into perspective. Performance I don't really need to talk about too much. I think we all know what the concept of performance is. Key to this talk, this is it right here, that's utilization. So utilization is a huge concern at Yahoo. For example, if I could reduce utilization, reduce the resources being used on our cluster by 25%, and I have a 25% growth that year, it means I need to buy no new hardware. And when you're running 35,000 to 40,000 Hadoop machines, I might be saving tens of millions of dollars. Another thought is you could actually be using the same piece of hardware and do 25% more processing if you could have that same reduction. So you could make that much more money with your algorithms and your data logic. That's the key here. I want you to think, that's one of the themes of the whole conference, right? If you had attended Jason Lau's talk on overcommit, it's like, how can we utilize these same machines more? If we can move from 40% to 65% utilization, if we can move 65 to 75% utilized using the hardware we have. Another key thought is just that as a big data company, we have existing hardware that's tuned perfectly, well, not perfectly, we all know perfect results, but it's bought in a certain balance of disk and memory and CPU. And Tez being a Yarn application kind of plays well with that same ratio on the same type of processing. So for us, Pig on Tez allows us to use the hardware that we already have and gain the performance that we already need. And of course, we know this virtuous cycle. If my jobs can be more performant, they're going to use by using less resources. That gives me more resources to run more jobs. And vice versa, if I have more resources available, I can increase my job's consumption and make them more performant. So it's a virtuous cycle of performance and utilization. benchmarks. Who attended a benchmark talk this week at Hadoop Summit where you saw numbers? Okay, a couple of you. Did the numbers always look good? Yeah, that's because benchmarks are tuned to look good. This is not a benchmark talk. In particular, you and I don't want to see a benchmark. What we really want to see is what the actual numbers are going to look like. What does it look like in reality? It's more like this, right? Shared cluster with resource contention. When things aren't going well, when there's bad disks and there's slow nodes and the load is high and there's reprocessing and you're up in the middle of the night with tight SLAs and money is on the line. That's the benchmark that you want to see, and that's the type of talk that this is going to represent. So our story began roughly last year in October. At this time, we had rolled out about 1% of our applications onto Tez. Not very much, but it's a toe in the water. Today, you can see we're a bit further. We're 70% with our expected full migration of all our pig on MapReduce jobs to Tez by July this year. A couple of things you should note is we run a lot of MapReduce jobs. We have a lot of pig scripts. The one thing I do want to point out is the number of applications. If you look at the 72% ratio, it looks a little strange. I know that people are like doing their math to say that looks like 50%, and that's because a single Tez application represents multiple MapReduce applications, right? There's a single controller, kind of going back to one of the onset goals of Tez. With that, this talk is going to get a little bit more technical, so I want to just introduce Rohini for the rest.
Thanks, Sean. Okay. So as you can see, we run about 200K pig script runs daily. It's not 200K pig scripts. It's like the number of runs. So each pig script runs every 5 minutes, 10 minutes, 15 minutes, or you have Harley jobs. So that's the amount of runs we have every day. So that translates to about like 1,000 plus unique pig scripts, probably a lot more than 1,000. And they are maintained by 100 different teams. So that's the way we run in Yahoo. So if we are going to migrate to pig on Tez, we were to go tell our users, okay, we're going to migrate, you have to make a lot of changes, you have to retune, you have to retest, redeploy, they're going to kill us, right? It's a lot of work, they are better off doing their actual work. So our unwritten rule was this: there's going to be no changes, your scripts will run as it is, we'll just push the new version, it'll switch from MapReduce to Tez. You don't have to change anything, you don't have to increase your parallelism or increase your memory or change your UDFs. So that was our goal. So with the volume that we had, like if we didn't do that, it would have been really a nightmare. So that was our goal, but we still had to do some changes. I'll talk about that later. Okay, coming to the rollout, how did we roll out? We rolled it out like any other major pig release that we have been doing for years. We always had 2 versions in the cluster, one the older version and the new version, and a version pointing to the stable one. So we are at .11 now. It's not exactly 11. It's like 11 closer to 13. So that's the stable one that was running. And what we do is we roll it out in a staged manner. We put it in staging cluster, turn it on as current and staging, then go to research and to production, which is very high revenue impact. So we bake it in each cluster, ensure there are no issues before we move on to the next cluster. If we discover issues, we go patch it and then roll it back. So this whole journey took us about 17 internal patch release for pig and Tez, and there were a lot of things we had to fix in Yarn as well because we were relying on the timeline server. So actually it was a lot better than the firefighting and the number of releases we had to go through when we had to harden Yarn. So it was, compared to that, this was like a lot smoother. So in case you're wondering about pig 14, so it's actually close to Apache pig 16. We started with pig 14, and users who migrated early, they use those versions in their share libs, Uzi share libs. So we had to keep that number. So the first thing we had to do when we did this migration was we had to provide equal feature parity with MapReduce. So we just translated all the MapReduce settings to equivalent Thais settings. So all the important ones were already covered. We had speculative execution, all the heap settings, container settings, all were done, like sort, shuffle, all the tuning was copied. And we mapped all the map settings to the root vertices and the reduce settings to the leaf and intermediate vertices. There were a lot of features that were not commonly used, and we ended up, as we migrated, we ended up finding that some users were using that, and without that they cannot migrate. So we went ahead and implemented most of them. There were a couple like MapReduce job class loader. We didn't decide to not do it now because that was only used in cases when like people had protobuf 2.4, 2.5 conflict and they put it in at that time. After now Hadoop has migrated to 2.5, they actually didn't need it. So we went just asked them to remove it. So that's kind of a change that users had to go through. So what else changed? So our user jobs, they had a lot of misconfigurations. We repeatedly tell them don't bundle any platform-specific jars, be it Pig, Hadoop, or HCAT jars. But they do it irrespective because when they do Maven assembly plugin to compile their UDF jars with all the dependencies, they just don't use scope provided, so it ends up in the dependencies jar. So all those users, you have .11 classes, .14 classes together, and you end up with a lot of like random behavior and unexpected failures. So this was probably like the most, and they had to go and fix that. And the other case was where you had container sizes were smaller than the heap sizes. This is actually bad, but still it worked in MapReduce because MapReduce was not so aggressive in using the heap. So it would still run. But what happened with Thais was it tries to use as much of the memory allocated as possible. So it would use it would go above the container limits, and the node managers would kill the containers. So this formed a bigger percentage as well. We try to do query and then find these jobs and tell our users to like fix it before they hit the error. So another case we had was this was like only one of two cases where people were using bzip for shuffle compression. They just do copy paste. They want final compression as bzip. They end up like changing the intermediate compression as well. So we didn't fix it, we just asked them to change, and we did fix it later, but we still wanted the users to change because you don't want bzip, which is very CPU intensive, to be your intermediate compression. So the other thing is like, people write bad code. So you do container reuse, which is like you're reusing the JVM, and what happens if you have static variables in the code. So they stay around and you end up messing up the values. So just take like a very simple program, you have a count, and you use a static variable for the count. So if the same class is rerun, so you're going to get really bad results. So a simple group by followed by count. This would work fine in MapReduce because the JVM is not reused. So but in Thais, you're going to get wrong results. And every run is going to give you different results because you don't know order in which the containers are going to be reused. So that's a problem. It's the problem in MapReduce as well. If you were to use the function twice, you would have hit this problem in MapReduce as well. So lucky for us, we didn't have like many cases of this. There were 2 or 3 cases of this. Okay, so and this impacted users a bit. So this was behavior change. The output files were not called part R000 anymore. So previously it was just the task index in the output file names. Now we had the number of the vertex, the output number, and also the task index number. So this was required so that the output files are uniquely named because you can have multiple outputs in the whole DAG. So Thais has the feature where you can, to the same output directory, you can write from multiple vertices. So the file names had to be unique, else they would get overwritten and you would be losing data. So users who had like hard coding the part names, they were using it for like as index files or dictionaries, they were like impacted. So they had to go back and like add a rename step so that they had the same file name as before. So that was one of the things that users had to change. So union optimization relied on MapReduce output base name. So this is MapReduce output base name is like something the file output format uses, and this is what sets the part MR or part V000. So this was introduced in Hadoop 2.x, and before like output formats written before, like during the 1.x time frame, they were just hard coding part M or part R. So those had problems, we had to get them fixed. So till they fixed it, we just turned off the union optimization, like if for like unknown output formats. So the other case was parsing pig counters. So with Uzi pig actions, you can go and say, okay, give me all the counters for all the child jobs this pig job ran. So what happened with those was like MapReduce, you will have like 3 or 4 jobs for a longer pig script. In Thais, there's only one job. So people were relying on, okay, I have 4 jobs, the third job would have this counter. So all that logic was broken. So there's only one job now. So they had to go fix that. And there's increased namespace usage with union optimizer. So the way union was implemented in MapReduce was that you had maps, you had reduced, let's say you do 2 group bys in the union of the data. So it will be written to disk, and then you have a map phase which combines about 128 MB of data and then writes it out again. So if you have a lot of smaller data, it got combined into bigger files. What happens in Thais is, since you have the ability to write from different vertices into the same directory, we just skipped that step. But what happened now was we had like more files. So in this case, there ended up being 40 output files. For some users, that was not like acceptable. They wanted like lesser number of files so that they don't hit the namespace limits. So they had to go turn off the union optimizer, or they had to go specify a parallel clause specifically to say like how many files they needed. So then here comes the dreaded out of memory. Yeah, so this is like one of our least favorites. So the Thais AM compared to the MapReduce AM is like had to scale really well because it represents a job of multiple MapReduce AMs. So it has to process more tasks, store more counters. So we always had a default 1 gig AM sizes in MapReduce, and most jobs used to run fine with that. So Thais needed more memory, so we couldn't tell the users to go change just for the AM. So what we used to do in Pig was calculate the number of tasks and go increase the memory. So if you add for every 5K task, we would add like 512 MB. So Pig code automatically incremented it so that you don't have out of memory errors. But still, even with that, we hit a lot of out of memory errors, and we had to go back and fix them, doing more optimizations to scale the AM better. Like, skipping storing 0 value counters, because you have like 100K tasks running in the AM. Skipping like counters was one of the memory consuming stuff. So things like that like helped us like scale well. And then another big problem with the AM was like now we were using the AM to just like send the task configs through RPC instead of distributing through distributed cache. So the AM had to really scale, and in our clusters, the jobs can run really wide. For example, 40K tasks can run concurrently for a AM. So you have to distribute that configs to 40K tasks. You really need to be like more efficient. So what happened was there were like a couple of things like hcat loader, which was stuffing way more into the configs, like it was duplicating config, putting all the partition split information, all that. So it was bloating up the config to 60 MB to 2 MB compressed, even which was a lot. So we were hitting a lot of out of memories. So all that is fixed, and this is not a big problem anymore. So the other story is like tasks ran out of memory. So there was a problem with autoparallelism. John will go into that in detail shortly. So other cases we had problems was map and reduce. So some cases were like in the MapReduce plan, like in the map we were doing in-memory joins. So what users would do is give more heap size to map. Usually it's reducers which have more heap size because they generally do a lot of processing and shuffle. But in these cases, maps had more heap size. And what ended up happening was in the Thais plan, those in-memory joins were happening in the reduce phases. So they didn't have enough memory because in-memory joins require putting the whole table in memory, and you need more memory. So those cases, users had to go make change, and then they had to increase the reducer heap size. Increased memory utilization due to multiple inputs and outputs. So with MapReduce, in map you have an output phase where like map outputs, and then reduce you have a shuffle input where you shuffle the input, just 2 sort buffers. You either had an output or an input. In Thais, what could happen is you can have both input and output, and you can have multiple of them. So that adds a lot of memory pressure. And to add to that, we turned on in-memory aggregation for group by default. So we did not do that before. We had put in a lot of fixes and we ended up turning that on by default. So with that, that added more memory pressure and we had to do better management of that. So if you look at this is 1 gig heap size that we generally have and 256 MB sort buffer, this is our default configuration. The jobs, that leaves like about 700 MB for the applications to use. If you take a Taze scenario, what happens is that you have multiple, they have 2 inputs and 2 outputs in this case. Just with that amount of memory, it's not going to work. If we had to divide the 256 MB by 4, it's not going to work. So what we did was we decided, okay, we'll use up more of the heap and leave less for the application, which generally worked. We took 50% of the heap, divided it between the inputs and outputs. And then again, like 20% of the heap was taken by the memory-based aggregation. So this was good, but still the performance was slightly bad. So what we did was, the inputs, once you fetch and sort them, you don't need those. We released it and then gave more to the output, so it became more faster. So coming to scale and stability, we have been running this for like from the beginning of the year at like a really scale, and like past few months we are like running at full thing. So it's been doing really well, really complex DAGs, processing terabytes of data from start to finish. It's working really well. We even had users run crazy jobs, like 300K tasks in one thing, and we didn't expect, but it did run to completion. So that was a surprise to us. So it's doing good. And stability, just one of our clusters run 50K jobs daily. They're just pig on Taze, not including hive on Taze. So it scales really well. We have been able to do a lot. And we have fixed a lot of issues with speculative execution, handling bad nodes, deadlocks, race conditions, a lot of issues. So stability is like taken care of now. So this is the kind of DAGs that we run. So most of the DAGs fall within like 15 vertices. The rest we have like still a long range, but like the volume of those are less, but they're really pretty complicated DAGs. Looking at this, 1 and 2, you only gain performance from container reuse, but as the plan gets bigger, the number of vertices grow, we get like lot more performance. So these are some crazy DAG patterns, the kind of things that Taze processes, we process with Taze now. Yeah, the second one is not my favorite. It's been given me a big headache debugging that one. So yeah, so we have very different kinds of patterns, all different kinds of jobs doing different things, group bys, self joins, distings, all like in a mess of them together. So, so it's been doing well. So coming to numbers, so if you had attended the keynote today, you would have seen this slide. So basically like, you know, applications have come down, runtime is really good. Utilization and CPU also has come down. So runtime, if you see, it's actually 400 to 500 hours per day that we are saving. This number is just for like one user. It was easy to take the numbers because they did the migration in like 2 days. So the numbers are like, looks more better. I mean, it's easy to see. And they have data varying through the week, but the pattern is consistent. So it's been really good. Individual job performance varies between 5 to 5x, but in total it's about like 30%. But 400 to 500 hours per day is like a huge number. For huge jobs, we see a lot of savings. But the utilization could still be a lot better. It was lower than what we expected. So some of the reasons is we just found out like a week back that speculative execution is causing more utilization. So what happens is in Taze, the task progress is not fixed. It starts running 0%, once done 100%. There's no progress update like in MapReduce. Speculative execution relies on that. So what happens, it sees 0 for a long time. Okay, you're not making progress, let me go launch one more. So we end up doing more speculative executions, and that causes more utilization. So the other thing that's happening is slow start. It doesn't happen with some part of the plans. For example, in this, you have a job reading from HDFS, but also getting a shuffle input from another vertex. So in these cases, it goes and starts as soon as the DAG starts. It doesn't wait for the other input to finish. Slow start basically says, okay, once a percentage of the upstream is finished, then start So we have it configured at 95%, but this just starts in the beginning of the DAG, sits there, runs idly, and then does nothing, so just wasting resources. Another thing is container reuse. We don't do exact match for container reuse. If you have bigger containers, we go reuse them, but it's not been such a big problem in terms of utilization, but that's one reason. So I'll hand it over to John to go over some more numbers. Here, John.
So Rohini was talking about memory and CPU and the like, but I'm going to be talking mostly about I/O and some of the features that interact with that. One of the promises of TES was we're going to be faster by trading HDFS bytes written and read for file system bytes written and read, which is a faster way of doing this, right? You don't have the replication factor. There's not the overhead of talking to, the chain of DFS. In this particular case, you can see, let's take a look at HDFS bytes read and written first. 20 petabytes saved on bytes written from HDFS, and also 20 petabytes saved on written to HDFS, right? So when you translate those, the 20 petabytes of read versus 20 petabytes of written, so don't forget the replication factor there. So there's 20 petabytes here, but 60 for written because of our replication factor of 3. So in total, we've saved read and written bytes of 80 petabytes. Again, this is one user on one cluster. You can imagine scaling this out for the rest of Yahoo. But we were a little surprised. So the file system writes increased by that much, but also a little more than we expected. Right? We traded HDFS for file, for local file, but there's a couple of pieces that added up to make it slightly worse. One is that the file system bytes read and written are shuffled data, right? One of the implications there is that TES shuffles more and also has more shuffle, right? More shuffles, but also shuffles more, right? When that comes into play with like autoparallelism, for example, the amount of shuffles that is needed is just incredibly high. It's going to hit the disk harder. So you're going to see. I guess my takeaway here is that you're going to need to take a look at your I/O from a holistic approach. If your I/O signature changes on your boxes, you're going to maybe need to retune your boxes and disks. For example, read ahead or write behind, and the scheduler for the boxes. It's something that needs to be looked at, maybe needs to be tuned, especially when you're pushing the utilization as high as something that Yahoo wants to be doing. Another thing is that since there's more data shuffled, there's a parameter in HDFS that is how much data is reserved for shuffle data. So you're going to need to increase that. In our case, I think we saw from the graph it was maybe 25% more. So we need to increase that number by roughly 25%. Another crazy DAG. You can just see also not only just that it's more performant, right? 39 minutes in TES versus 1 hour and 15 in MapReduce, but also that the optimizations were in place allowed us to do it with less tasks. So 22K tasks versus 45K tasks. So we're not there in I/O yet either. A couple of problems that we still face are like what Rohini was talking about, multiple inputs and outputs. It puts so much memory pressure. And when you combine that memory pressure with new features in TES, it can cause problems. Data skew is a classic big data problem. We'll address that just in a bit. And I'll go into more detail about autoparallelism. So this group by is a really common operation. But when you take it to the very extreme, this is 59 group bys, right? Group by on 59 different dimensions. And the optimization that we put into place for TES actually backfired at this scale. And so you have to be careful about optimizations that don't translate well to scale. This is one of those cases. The 59 outputs puts an incredible amount of memory pressure on that one tiny vertice that's feeding all those 59 stages. And so it doesn't have enough memory to do the sorting correctly to send all that data to the downstream. It ends up being a problem both there, but also on the receiving side. So the vertice that's at the bottom that's receiving 59 inputs, it also has a lot less memory to be doing, to be working efficiently there. It's going to be spilling a lot to disk. This is just worse than in MapReduce. So for a case like this where it's scaled out, we're better off reverting to the old MapReduce implementation, which just tags records in a MapReduce stage and multiplexes them, demultiplexes them to do it in that manner. And for inputs greater than 10, outputs greater than 10, that's exactly what we're going to be doing. So there's another case in TES that happens, and that's data skew. We see this in MapReduce, we see this in TES, but in TES it can be worse if you're not careful. One of those cases is with self-joins and one-to-one edges with unordered writers, unordered output. What can happen is that your skewed data goes to one reducer, and then it passes its skewed data down to the next set of reducer, also skewing it. So it's essentially a chain of skew. And so you're amplifying the skew a lot, and the processing times can be really long. MapReduce fixed this. The way it addressed this problem is essentially writing intermediate results to HDFS. And so then when it read them again, it resplit them, kind of fixing the skew. It traded performance to do this. So in TES, we need a different implementation. So the implementation we're going forward with is going to be done by Twitter, and we're looking at this as a really eager optimization, something we want to pull in soon. That's called the fair custom data routing. In that, it basically takes the skewed vertices, the skewed reducers, and chops them up into smaller pieces, and then maybe later combining those. That's the way that I think TES is going to go forward addressing data skew. So autoparallelism is a feature that only exists in TES. In essence, it changes the amount of reducers to right size the data by shrinking that number. Maybe in this case, here's the classic MapReduce algorithm: 3 maps, 3 reducers, and 9 shuffles. In TES, if we auto-reduce those 3 reducers down to 1 based on the input size, you have to send all those 9, that one lone vertex, one lone reducer, 9 messages to tell them about the 9 fetches they get. This doesn't seem so bad, but imagine running at Yahoo scale. 1,000 maps, 999 reducers. That's nearly 1 million messages you need to send to that lone reducer. That's nearly 1 million fetches it has to do. And once it's done with those fetches, it has to merge them all together. Even our scale has scale. So what are we going to do? This is a 2-pronged approach, actually 3-pronged approach. One is we're going to improve messaging by creating a composite message, a message that can send more dense information. In this case, one message, each reducer will receive 1 message from each map. In addition, I'm going to skip over the empty partitions, but we're going to implement a custom shuffle handler, much like what they've been doing in Hive and LLAP. Even though we're only sending that 1 message with the composite, we're still fetching the million pieces, right? The custom shuffle handler is going to allow us to fetch those 1 per map. So in that case, 1,000 fetches, which is much easier to deal with than a million. Another alternative approach is to do an in-memory merger. So instead of merging the data and writing to disk and spilling to disk and being slow, we can aggregate those merges in memory and reduce the number of spills. So I guess in summary, you could say our ride in Pig on Tez was a little bumpy. It was longer than expected. But now we find it to be smooth, and the transition customers are making are much better than before. There's still blockers, don't get me wrong. There's still people that can't migrate due to feature lack, but we see the performance. And not only do we see today's performance, but the amount of optimizations and the potential for optimizations in the future is still great. You can customize almost everything, and we see better algorithms and new crazy ideas coming from the community that's just going to benefit everyone who's using Tez. Particularly, we're interested in coming up is DFS Shuffle. We're interested in cross-product edges, and also a new limit optimizer where we can, once we have enough results, we can stop processing instead of processing the full and waiting for this full result. I guess I want to just humbly thank everyone who was involved. I mean, the number of Yahoos, like Jason Lau, Koji, but all of them, all our pig users at Yahoo, all of the people that put up with me and Rohini, and all the people that keep us honest. Also, the good folks at Hortonworks, including Daniel Dai and Bakas and Sid and Nitesh. Thank you for helping us along this journey. Thank you very much. So I think we probably have time for maybe one, maybe two questions. But if you could come up and ask us, I'll repeat it and we can try to get an answer. Yeah, one of the features, good question. The question is essentially, when you have, so MapReduce jobs are broken into individual pieces, right? So the intermediate data is cleaned up after each one. Tez is one DAG, right? So the intermediate data is cleaned up at the end, right? So he's addressing a problem that there's actually, for long-running jobs, there's a lot of extra intermediate data. And that's a great question, and it's right on point. When we looked at the custom shuffle handler from LAP, that's exactly one of the problems they're addressing. And so there's a new set of messaging that you can send that says, for this part, I'm now done with that intermediate data. Clean this up. Even though the job isn't done, even though the application hasn't finished, this piece is finished. And so it's a new messaging that, of course, we don't have right now, but it's a future work.
Yeah, we actually don't run into this problem. We haven't faced this. We have enough shuffle space. It's not been a big problem for us.
Other questions? All right, tell you what, Rohini and I will be around, probably sitting outside. Come find us, and we can have those individual conversations offline. Thanks again.
Thank you, folks.